So what I'll do every week is to do some questions. It's great for people to ask questions in advance. If you got any, and that means that even if you can't attend live, right document up. So even if you can't attend live, you still can ask questions and benefit from it. I'm Michael Kemp. So I'm the lecturer for this subject. So how this sort of system works is you can see my main screen, so you should be able to see it on the middle there. Depending on how your screen size is and mine, it can come out a bit funny. So if you you can make it bigger and zoom in, etc. You can do this if you're recording too. So approximately up here somewhere, on my screen at least, just above it, there's a button that says full screen. If you press that, it makes that part bigger, which makes it easier to see. It does hide the chat box from you, so you just need to minimize it, but that might be useful. You can zoom in and things like that at various points in time, so you might find that a handy feature. If you've got any questions, feel free to interrupt. You can use a microphone if you wanted to. So again, there's an icon maybe about here. It looks like a microphone. If you click that, it allows you to turn your microphone on. It's normally best to try it, before the outside the meeting time, make sure it's all okay. So ask questions via voice if you want to. If you do connect to your microphone, please mute it if you're not using it. Otherwise, more than happy for you to ask questions in the chat box or in advance if that's easier. So this is supposed to be for you, so let's try to have some, if you can ask some questions as we go along, that's great. So first of all, let's just do a bit of an introduction. So the topics in calculus is the name of the subject. Pretty much it's trying to extend the analytical methods that you can use to solve differential equations and partial differential equations. So that's pretty much what we're going to do. So we look at systems in chapter 1. Chapter 2 is focused around the Sturm-Liouville problems. So, and looking at special solution, a few solutions of those. So Bessel's equations is the key highlight there, and looking at Frobenius method as a way of trying to actually work out solutions in some of these instances. Then 3 and 4 are looking at Laplace and Fourier methods, which are both methods for solving differential equations, of which you've probably seen some of them already. But we're trying to extend them. So certainly Laplace, you've seen a little bit, but we're trying to extend it. In particular, how we extend it is in terms of discontinuous functions. So you've only dealt with continuous ones primarily in, say, Maths 220. And then once we've got all that, we're going to put all these together to try to solve partial differential equations. So those differential equations, we've got partial derivatives, not just normal derivatives. And things like Laplace, Fourier transforms, all crop up in those. And again, you can even have systems as well, although there's a limit to how far we can go, of course. So that's sort of in a nutshell. So the first section of the subject, call it chapter 1, is looking at how to solve systems of linear differential, solving systems of differential equations. So I've got an example one on the screen here. So this one is called the SIS model. So this is a way of modeling how diseases, so like a disease, so an infectious disease spreads in a population. So this one's called the SIS model. It stands, S is for susceptible, so people who can get the infection, I is for infected. And why it's called SIS is because if people get infected, if they recover, they go back to susceptible again. So it's a simple model. More complicated ones is susceptible, infected, recovered, and there's various forms of that. So being able to write it as a system allows you to easily modify, add extra letters as you need to, quite easily. I want to keep it simple just because I want to do things with it later. So the way of modeling this nicely is in terms of 2 letters, so both the number of people that are susceptible and the number of people that are infected, so S and I respectively. and just trying to see how those things change over time. And so if you're susceptible, then if you bump into infected people, there's a chance of getting infection. So this term here is reflecting the essentially the rate that people get infected by bumping into each other. So S times I is how many people you bump into each other and some sort of rate. Then the other term that you see here, this later one here, is the number of people that are infected that then go to recover. So the minus I alpha is all the people that are infected but now recovering, going back up into the susceptible range. And there's a slight change here just to make sure that the long-term population is capital N. So there's a birth-death effect in there as well, in a small way. So being able to have a system allows you to model many letters at the same time. And so you've dealt with when you've got one variable, so say just S by itself depending on, say, time. So one dependent variable, one independent variable. Looking how to solve those. You've done some of those things, Maths 220. So now we want to look at how you solve an ordinary differential equation when you've got several letters. Now, with lots of these equations, you can actually simplify any system down, a lot of systems down into situations into just what you've already dealt with. But it's good to deal with systems in their own right. And indeed, given any second order, third order, fourth order, etc., ordinary differential equation, you can convert it into a system all of first order differential equations. And so understanding how these systems work helps you solve lots of things. I guess that's where we're going from. And so where we want to head towards is to be able to try to grapple, understand equations like this as much as possible. Now, this is nonlinear. It's got an S times an I, for example. And nonlinear differential equations tend to get pretty difficult pretty quickly. So this particular one is solvable. So you can find an analytic solution for this one. I won't do it. But as soon as you make the model more complicated by chucking in recovered people, for example, it just becomes intractable. But seeing the techniques that you can apply, so working at where it's stable, giving you an idea of the qualitative understanding of dynamics is quite important. So the stepping through the chapter is we want to start with the easy ones, easy cases. That's linear differential equations. And let's make them really simple. Let's make them homogeneous. And if you start with homogeneous linear differential equations, look how to work at how to solve them, understand the stability. Then we'll see, so then there's two different directions we can extend this. One is to look at nonlinear ones, which is this an example of nonlinear. And the other sort of example we can do is we have a linear differential equation, but it's inhomogeneous, and how to solve those sort of things, and how to get a sense of stability for those as well. So that's broadly what we're trying to do. So again, any questions, fire away. So let's have one example. So I've got a differential equation, so second order, of which you've probably you might be able to know how to solve directly. But I want to show you how it fits into what we're doing here, and the methods here will just help us illustrate something. So what I want to do is, first I've got a second order differential equation. Let's write it down as a system of first order DEs, ODEs even. How do you do that? That's my first question. So can any one of you tell me quickly what you would do to try to convert this into a first order system of DEs? Yeah. So I would make a new variable up. So I haven't made it really clear. Let's assume that y is a function of t, say, make it easier. And so let x be a new variable and make it equal to the derivative here. So and that's exact as Brett said. And so in general, if you've got a system of second, third, fourth, etc. order, then you just make lots of new variables defined to all the different derivatives and let them equal to all the different derivatives until just before you get the top one. So if it's third order, you do x equals y dash, another variable w is equal to y double dash, etc. Then you write down everything you've got. So the now you've got variables x and y. We want to make them DE, so we look at x dash and y dash. They're the two sort of things we need to consider. So let's try to think what they are. So x dash, well, by definition, that would be y dash dash. That's y double dash. And you go, well, I can write that down using this top equation. That's the one I've got at the top here. So that's going to be equal to, rearrange at the top, 4y dash plus 4y. Now, what we want to do is we write it in terms of x and y. And we go, well, y dash, well, that's great. I know that's just x. And y, well, that's fine. It's already in the terms we want. So x dash we can write down as 4x plus 4y. But the real heart of it is to remember that. And yeah, pretty much sweet, I reckon. Now, y dash, what's y dash equal to? Well, by construction, y dash is just equal to x. That's how we set it up. So the one that requires the most work is this top one up here. Everything else is just a simple one. So what we can now write out more succinctly is a x, y is our variables. The derivative with respect to time can now be written as a matrix. So 4, 4, 1, 0 times by x, y. So this is a linear differential equation and it's homogeneous. So there's everything being described by the matrix essentially. So let's have a go at trying to tackle how to solve this and how to work out stability at the same time. So stability is easier than anything else. So firstly, let's look at so critical point. So a critical point is when the derivative is equal to 0. So these are points where the system isn't changing at all. And so there's it's not moving, which is good. And if we want to know, so points that aren't moving can't be stable. So the critical points are the ones that can be sort of stable as such. So when you've got it to be homogeneous like this, if I write this down as AX, for example, so we've got AX is equal to, if this is equal to 0, if you take the inverse of A of both sides, that implies, for an invertible matrix at least, that our solution has to be just 0. So for a linear system where you've got an invertible matrix, then the only critical point is x equals 0, y equals 0. Or back in terms of this original one, y is 0 and the y dash equals 0. What do you think of that way? That's our critical point. So let's try to work out if it's stable or not. And we'll also, in our back of mind, we want to try to find the ultimate solution. And the real heart of it is about eigenvalues. So the eigenvalues of this matrix really are the key features. So we're going to try to find the eigenvalues of this matrix. So how do you do that? What's the first step to finding eigenvalues? Again, let's see if I can get you. It's not a rhetorical question, so see if you can type in something. So I write the characteristic equation. That's right. So let's take the determinant of this. So determinant of this would be of you subtract lambda from all the diagonal entries. Yep, just as you wrote down, and take the determinant one. So before minus lambda times by minus lambda minus, let me write it down properly, 4 times by 1 let's make that a positive. Sorry, I should have. Just really, I think I didn't write this down properly. there you go. Doesn't change anything so far, but it will in a second. So I make that a minus, that's better. So it'd be minus 4. And so if you then expand the brackets, you get something like lambda squared minus 4 lambda plus 4. That's better. And you factorize it, so you get lambda minus 2 squared. Now, I could have done it how I wrote it initially, but I just want to emphasize something else here. So what are the eigenvalues? So can you tell me what the eigenvalues are? Yeah, it's just 2. There's only one of them. Now, it's got a multiplicity of 2, which is what you both guys suggested. And so let's write down 2 and 2. So let's work at stability and we'll work out how to solve it. So the way to work out stability is looking at the eigenvalues. So if they are positive, it suggests that along the directions of the eigenvectors, so to speak, or at least in different, so in the directions from the critical point, positive values suggest it's increasing away. Negative values tend to suggest that it's approaching towards. So the fact they're both positive tells you that whatever direction you pick on at all, it's going to fire away. So that suggests to me straight away that it's unstable, because no matter which direction you are, it's going to head away from the critical point because they're both positive. And because they're all going away from every single direction, it's a node. And so if you look at the critical point, it's always going to go away from that thing. And it's a proper node in the sense that any direction is possible, is the idea. If they were both positive but different values, then it's an improper node, as in they tend to disappear in just one key direction only, rather than in any particular direction. But it's still unstable. If they were both negative, that would suggest they're being stable, so always heading towards. And you get other things as well, of course. So we'll just stick with this one for the moment. We'll see some others as we go through. So that's the stability. So critical point, and we know that this critical point, so that's the origin here, is an unstable node. Well, how do you find general solution? Well, now since you've got a repeated root, so if all the eigenvalues are distinct, then pretty much the answer looks like, some vector c times by e to the eigenvalue 2t. And it's just a sum of all these different ones, one for each different eigenvalue. And you'll see shortly the vector in front of it is the corresponding eigenvector. That's what they normally are. When you've got repeated roots, you can get some funny things happening. That you get another sort of thing happen. You're going to get other sorts of cases happening. So when you've got a repeated root, the other solution you need to do will look the same sort of thing, but it'll have a t out the front of it. So I could have another vector d. So as we'll see shortly, c is going to be related to a what do we call it? An eigenvalue, an eigenvector. So you get some eigenvectors cropping up. And so C and D will somehow span all the space, but we'll go through it carefully. So instead of trying to remember exactly what the pattern is, let's just try this solution. So as soon as you get a repeated root, let's write that down. So I'm doing this process for repeated root. So when you get a repeated root, then this sort of thing. So just as a digression, can I I've got a C and a D here. Can I find the first eigenvector normally? And the answer is, yeah, I will do so that anyhow. But it's good to see, instead of trying to remember every single aspect of the process, it's good just to have a guess for this and then go through the process and go, oh, bang, oh, that one's going to be that's going to be my normal 2 eigenvector, which will work at my normal way. So let's just see how things pan out. So we know we got our derivative, so what do we call them? So we'll call them x before. So the derivative of our x and y is equal to my matrix, which I'll call A for the moment, times by original vector. So that's basically what my differential equation looks like. So let's do both forms. So firstly, let's find the derivative of this. So I take the derivative, we'll just direct time. So that would just be dump the 2 down the front. So 2c e to the 2t. Plus now, when you've got a t e to the 2t, so if you just differentiate the exponential term, you're getting 2 dt e to the 2t. If you differentiate the t term, you're getting plus d e to the 2t. So on the other hand, a x here is just the original matrix times all this sort of stuff. Now, I won't work out what a is just yet, I'm all in a second. So a to the 2t is just a scalar, so it's a c e to the 2t plus t e to the 2t times by ad. Now these two are equal. So what I want to do is I want to equate coefficients which are the same. So you can see that in our first form we've got a t e to the 2t. So any t e to the 2t terms want to match up. And for the other one like that is just that one there. So we'll make sure that the coefficients in them are the same. The second thing we want to do is the other terms, which is either 2t, the coefficients of those also match up. So for the ones in yellow, these ones first, so we've got AD is equal to 2D. That's what you see for those coefficients. And that tells me straight away, well, hold on a sec, A times the vector is equal to a scalar times a vector. That just tells you that D is a 2 eigenvector. And the way to solve that, as you say, is just solve it like normally. So in general, I'll skip some calculations here. So C1 times by 2,1 is sort of the general, let's make it A. Try to be careful with my letters here. Yeah, that would be the thing. So what does a 2 eigenvector mean? So a 2 eigenvector is an eigenvector with which matches up the eigenvalue of 2. So the 2 here just tells you what the eigenvalue is. That's all that. So the fact that, so the 2 here matches that 2, which is the eigenvalue. So after a little bit of work, as you would do normally, this is the general eigenvector, and you can let A be anything you want to at all. So A is going to be one of the constants of integration, so to speak. So what you could do is you could just let A equals 1 temporarily, and then chuck it back in at the very end. But I'll leave it there for the moment just to sort of see what it does essentially. So A is just a constant of integration. So the one in green, so the green equation gives AC is equal to 2C plus D. That's what all the green bits, that's the coefficients of the green bits put together. So in order to try to solve this, you've got to put all the D you know, so we do D, we know what that is now. I'm over here. And so now we've got to put all the C's together. So anyway, it's going to be A, and the way to do this is in order to try to combine the C's together, let's put them all on one side for the moment. one or just what D is. So D is the A21. So that's what it looks like in general. Now, in order to try to combine these together, I need to chuck an identity matrix in here to make it match up. So it's A minus 2I times by C is equal to our vector over here. So A minus 2I, well, this is the sort of, this expression here, you actually work out when you're trying to find the two eigenvector. When you have to work the eigenvector, you work the same expression out. They match up for a reason. So A, if we recall, was 4 minus 4, 1, 0. So I had above. So subtracting, minus 2I just means subtracting off 2 off the diagonal entries. So it'd be 2 minus 4, 1 minus 2 times by C, I don't know, let's call it, I run out of letters here, if I'm not careful. So maybe I should call it C1 and C2 are the different components of this vector C. That's going to be equal to 2A and A in general. And now we're going to try to solve this thing here. I would try to do some things. How these things always work out is there'll always be a, so you can always, if you do get reduced for echelon form, there'll always be a row of zeros down the bottom. That will always happen because how things have worked out, because we know, because 2 is an eigenvalue, that'll always happen. So if you do, you know, row 2 minus 2 lots of row 1, that top row would disappear to 0. I'll just write down what I'm doing. So I do row 2 minus 2 lots of row 1. That'll kill the top row, which makes it all zeros. And it's good just to check that in your mind at least. And then you can swap the first and second rows if you wanted to get pure reduced echelon form. So it'd be 1 minus 2, 0, 0. C1, C2 is equal to A, 0. So it's after doing some row operations. So that's reduced echelon form. And when it's in reduced echelon form, then we can sort of just read off the answer, essentially. Depending how good you are reading off, it does depend on your practice. You can read off quickly what I'm doing here immediately. So what I would do is look at all the columns here which don't have a leading entry in it, which is this column here. So then I would let the corresponding variable, which in this case is C2, equal to be a parameter. So let's call it B, say, sensible names. So then this top row then says, you've got C1 minus 2 lots of C2, which I'm calling B, is equal to A. So I can see that C1, which is the vector I want essentially, is equal to A plus 2B, rearranging the equation, and C2 is equal to B, or putting in vector form, this is to A outside of, say, 1, 0, plus B outside of, say, 2, 1. If you want to. I mean, I mentioned this, I mean, there's nothing wrong with the original form, by the way. So you can make, so the A here matches up to the A at the top here. So there's a connection between those two. So they've got to be the same variable, which is why I've left it round. So you notice this 2, 1 here crops up from before. That happens to be the eigenvector from earlier. So this expression here, so any of these things, so all of those expressions, and so for example, 1, 0 being one of them in particular, are called generalized two eigenvectors. So these are the generalized eigenvectors. And they sort of crop up in these sort of fashion. And so you can write things more succinctly down if you wanted to, but this gives you the rough idea. And so the generalized eigenvectors, so 1, 0, and the original eigenvectors together span the whole vector space. Depends how much linear algebra you remember, if you know what I mean by that. So let's put it all together. So we know the original solution looked like that. We worked out what D was. So D was that vector down here. We worked out what C was. That's what I've written down before. So therefore my general solution, so can now be written as, so Y, which is what I'm trying to work out, and again it's, if you think of it as being XY here, is being equal to this vector C times by e to the 2t plus a vector D, which was 2aa times by t e to the 2t. And that's our general solution. So I could put a tick here, so well, I guess that's right. It's probably worth expanding, so it's a plus 2b e to the 2t plus 2a 2 to the 2t, and the bottom one here is b e to the 2t plus at e to the 2t. And in particular, I guess the thing that we want to know is the y variable is equal to that expression. And again, if you think back to a really top of the question here, we wanted to know that equation. So we want to know what y was in this particular case. So that's a really long question. And so let's just clarify exactly what we did there. So there's a few aspects. So the first step was, given any differential equation, we can convert it to a linear system if we wanted to. So that was the first step. So that's one little mini problem, really. Other problems we did just individually was looked at critical points, which really just, for a linear homogeneous, that's really just going to be the origin all the time. To try to work out stability, we worked at the eigenvalues. And so from the eigenvalues, you can work out stability from that. That's one thing we did. So the other thing we did was try to solve it. Now, in general, the way to solve it is to work out eigenvectors and eigenvalues, and you always need them. The harder case to do of all of them, I think, is the repeated roots, where you have to do a little bit more fiddly work to try to work out the full solution. So that's what I did just here, because that's the hardest of them. Other cases, I think, are not involved, because you can just simply work at eigenvectors directly, and fantastic. So when I work at repeated roots, I know that the solutions would be some vector times by e to the eigenvalue 2, eigenvalue t, but I also, if I've got repeated roots, I have to put a t as well and have the same sort of term but with a t in front of it. If I had a triple root, so 2, 2, 2, it'd be a t squared, either 2, 2 is 2t as well, etc. And then, so I don't have to remember absolutely everything, I actually just sub that into my original equation, equate matching coefficients, and solve various equations. Now I am expecting, when I do that, to have to get an eigenvalue cropping up the process. And in particular, you'll get it pretty quickly. It's the very first equation to solve will give you the eigenvectors, which you'd solve just like you do normally. And then after that, you then solve the generalized one. So I've written it in full general terms. What you could have done is, instead of having an A up here, you could just let A be 1, make things a bit easier. And then solve for the corresponding, and then just solve for normal and just find a solution. So just let 1, 0 be one of the solutions, for example. And that together would form one solution to the original equation, and you just chuck a variable to a at the front of the whole lot of it, and that would be one solution then plus B times by the one that corresponds from the normal eigenvector solution, which is essentially what we've got here. That's a different way of doing it. So you just need a basis of the solutions. So one basis element is e to the 2t times by 2, 1, and the other one's got all the other two, is all the a terms put together essentially. So that's an overall idea. So let's see how I can go with tackling these few problems here. So I've got two more I was hoping to try to do. Let's see how I go. Next one, this is the page 40 something of the 2, I think it is, of the study guide. Page number has changed. So this is the example that's given. Okay, let's see if I can do it quickly. So pretty much this is saying you've got a vector y. I should define these things. So y is y1, y2, and let A be the matrix of coefficients. So 1, -5, 1, 3. So this is saying y is equal to the matrix A times by the vector y, so the derivative of it, plus some other bits, so 0, 8. So this is an inhomogeneous equation. So what I'll do next week, in next week's online meeting, I'll look at methods to solve inhomogeneous methods in general. But I'll just look at this one special case. Let's just try to solve it. And let's just take a step back. Let's try to work out critical value, critical point. So critical point is when the derivative is equal to 0. A y plus 0, 8 is equal to 0. And now you can solve for y. So let's call it y naught at my critical point. So y naught, then if you solve this equation here, would be equal to the inverse of A times by the negative of 0, 8. And after a little bit of work, you'd get the answer -1, -5. And there's lots of ways. You can solve, you don't actually have, as a matter of fact, it's slightly quicker. Oh, well, in this case, I don't think it really matters too much. But if you solve it, in general, trying to solve it the linear system directly rather than using inverse is actually quicker, believe it or not. But in this case, because it's 2 by 2, you know the form of inverse quite well. It doesn't hurt you, really. But it is quicker not to actually have to do the full inverse, but never mind. So that's the answer. That gives the critical point in this case. And so here's my little trick. So when you've got the linear system there can be equal to A times by y plus, well, 0, 8. What 0, 8 is, well, I've just worked it out to be, essentially, looking here. This is equal to minus A times by my critical point. And so what I can do, when you take derivative, if you chuck it in a constant law, take derivative, it doesn't just disappears. So you can factorize the A out. So y minus y naught, so my critical point, which is this -1, -5 over here, derivative is equal to A times that. So by subtracting off the critical point, I've made it homogeneous. Now, in terms of what I'll do next week, using the method for undetermined coefficients, essentially what we're doing is the particular solution we're guessing is letting y be a constant function, and then you end up solving that and realizing this constant A happens to be the critical point. That's the way to do it, how I'll present it next week. And again, you might find much more happier doing that. So let's make it easier. Let W then be y minus y naught. And so what we're now left with is my new vector W is equal to the matrix A 1 minus 5, 1, 3 times by W. So I've just reduced it to a homogeneous case. Now the heart to doing this, as always, to work at stability and to work at general solution, first step is to find the eigenvalues. And the eigenvalues, to find eigenvalues, as we said earlier, is to subtract off, is to work out the characteristic equation, solve it. So in this case, you're only getting 2 plus or minus 2i. So I'm cutting up quite a bit of steps. It's a bit of work there by all means, but I'd like you to try to practice that yourself. Let's get the bigger picture. So when you get complex eigenvalues, a few things, let's have a little digression. We'll talk about stability here. So as soon as you get complex eigenvalues, it means it spins around essentially. So you've got some sort of rotation happening. So the real part determines what happens to it. So you got a critical point. So a critical point here is -1, -5, if I recall correct. So that's our critical point. The fact it's a 2 here, positive values means that the values are increasing, so it will go away. So it's spinning around, going away. So what will happen then is this will be a unstable, because it's going away, and it's a spiral. If the real part here was negative, it means it'd be spinning around, going inwards. It'll be spiraling inwards. So it'll be a stable spiral. And if the real part was 0, it means it's spinning around but not going in or going out, and so it just ends up being a fixed orbit. So we'll call that a center. And again, it's stable. Now, when you jump to nonlinear, by the way, the spirals transfer over nicely, but the centers, they aren't guaranteed of remaining as centers when you go to nonlinear situation. So you're not quite sure what happens. But eigenvalues, as you can see, are a key thing for stability. So the stable mean it's going away from the critical point and vice versa. So stable means that in a dynamical sense, if this is my original differential equation, right? I'll do this one here. Let's make it more critical situation, more concrete situation. So this is the example I mentioned at the beginning of the class. So this is a population of people. We've got 2 groups of people. One is susceptible to catching a disease, one people are infected. And so for a disease, one critical point which makes sense, hopefully, is that everybody's susceptible but no one's infected. So there's just no disease present. That's a critical point. Now, if the situation remains like that, so there's always, if you don't have any infected people, then nothing's going to happen. It's just exactly fixed. So critical points in themselves, if you happen to land exactly on a critical point, nothing ever changes. What happens though if you bump it slightly? So in this situation, what happens if someone flies in from another country, and one person comes in who's infected? You just vary the point slightly. What's going to happen? So if it's stable, that means that it will go, that even though you've changed the system slightly, it will go back to the critical point. So if someone flies in from overseas and they're infected, a small change, the system will quickly fix itself up and the disease will disappear. So everyone will get over it and come back to normal. If it's unstable, then it still might end up going back to the critical point, but there are quite a few paths which lead to a change in state. So example for this infection case is, say someone flies in, the infection might grow pretty quickly and then become an endemic. So it might end up never leaving the population. So there was nothing before, but they introduce it and it keeps going in. And that's like the idea of a common cold, right? So Aboriginals perhaps when this country, before Europeans came, it didn't have the common cold, but when the Europeans come and introduced it, and now it's permanently in this situation. So that would be an unstable critical point because a slight disturbance to the system has moved it very far away from the previous critical point. That's the idea of stability. Now there might be some situations where a disturbance doesn't change it much or it stays the same, but sometimes it does. And if there are some instances where a big change can happen, we call that being unstable. So that's the idea. And again, it's easy to see in this more concrete example. Got any more questions? Fire away, of course. So back to this one, we know we've got an unstable spiral, so it means it's spiraling away. So the next thing we're going to do is to work out what the solution is. So the way to do that is to find the eigenvectors. Now, because we have the original equation's real valued, the complex, you've got complex solutions, they occur in complex conjugate pairs, so you've got plus or minus I aspect. It also means that you usually have to work at one eigenvector and just pull it apart. And the reason is because the eigenvectors also form in complex conjugate pairs. So if you find one, you've also automatically got the other one. I'll just skip along a bit. So if you've got 2 plus 2i as the eigenvalue, then you can work out what the eigenvector is. And did I write it down? So there's a little bit of work here. So there's more than one writing it down. So minus 1 minus 2i 1, for example, is one way of writing it down. You could alternatively write it down as 5 minus 1 minus 2i, I think it is. If I got it right in the right way. Yeah, so these are these two are actually the same, except they differ by a scalar multiple. So either form's fine. If you take one approach, the final length looks quite a bit different to the other one, but they're equivalent. So you can pick either or. So I'll pick this one because it looks slightly nicer to me, but up to you, of course. So the basis in terms of complex numbers then would be the eigenvector times by e to the eigenvalue times by t. So that would be one basis solution for our original equation. And because it's in complex conjugate pairs, it's that one as well as the complex conjugate pair I, just replacing I by minus I. So that's the two bases is that, essentially. So just up to plus or minus over everything. So, and again, if you find a linear combination of those, so A times that plus B times the minus the other case, then you get, that would find all solutions. For W, the issue though is it's got I's everywhere, and original question didn't. So we should get rid of it. So the way to do that is you want to get a new basis, and the new basis pretty much is you just take the real part of that and the imaginary part of that, and those two together will form a new basis for all the solutions. And the benefit is, because you're taking real and imaginary parts, they would be real functions now, which is great because that's what we want to deal with. So let's just work at the real part. So let's look at this one here. To try to spell out a bit more. So let's just do the, make it simpler. Let's make it minus positive here. So that's what I originally had. So if you expand this thing out, minus 1 minus 2i 1, e2 plus 2it, that's either 2t times either 2it. 2it is complex valued of cos 2t plus I sine 2t. And let's be careful, the e to the 2t, I'll put it there somewhere. So that would be my expansion for it. And now you've got to expand it out. So if you collect just the top row, so you're getting -1, so you just collect all the real terms, so -1 times by e to the 2t cos 2t minus 2i times by positive I gives you positive 2 e to the 2t sine 2t. That gives you all the real parts, and then the imaginary parts would be minus, so plus I, sort of minus 2 e to the 2t cos 2t, etc. Oh, I should put it down, shouldn't I? It's not that hard. So minus e to the 2t sine 2t. That was and then something for the second component, so just on the first component here. And so the real part would be just everything without an I in it, and so that would be the u vector, and that would be the first basis solution for it, and everything with i's in it over here would be a form v, and that would be the second basis solution. And then the solution we want at the end then, the solution for w would be, I don't know, say c1 times by u plus c2 times by v, once you work out what they are, right? And lastly, our original question, if you go all the way to the top, was to find what y is, and we said that y was equal to y minus the critical point is equal to w, and so y is the w plus our critical point. And so this is going to be equal to this, whatever we got over here, plus our critical point, which we worked out was -1, -5, well and truly above. So taking a step back before I do this last question quickly, is that to find the solution, you really, critical eigenvalues, eigenvectors are super important, absolutely. If you get a situation where you get complex values, that's the other harder of the cases, then just only have to work at one, because they find complex conjugate pairs, and work out the real and imaginary parts of the solution. That's what I've done here, and then they will form the new basis, essentially. That's the key trick. So the situation I haven't covered is where you've got two real eigenvalues which are not the same. That's the easiest of the cases, which is why for the sake of time, I haven't done that here. Now, I say it's easy. As you can see, all these calculations have been quite involved. I mean, you can more than a page is not uncommon for some of these things, as you can see from my work. So it's all relative, I have to admit. And the difficulty is just to make sure you remember all the process. So as I said, the overall process, eigenvalues, eigenvectors, put them together to find the basis solutions, and then just take a linear combination of all of those. Why don't you use the second row view? Because of the sake of time, you should. So yeah, there's more work in here. So there's, I mean, again, I picked the harder one. So you really should do more. You're absolutely right. I just got 5 minutes when I want to cover one more example. So that's the reason why I've missed it today. So I exercise for you. Let's put it that way. So the last case I want to try to cover quickly is this epidemic modeling. So this is the CIS model. So as I said, S and I is susceptible infected. B is a measure of how quickly the infection grows, and A is a measure of how quickly people recover, essentially. So it's a nonlinear model, and although this particular one happens to be solvable, if I change it slightly, then it doesn't become that anymore. So I want to look at how to so nonlinear systems in the general tend to be pretty hard to solve. let's try to work. It's just what I would like to do is just get a sense of how can I work it if it's stable or not. So key things for this is working out critical points. So let's do that first. So critical points are basically when both the derivatives are equal to 0. That's when a critical point is going to happen. Now, in this case, if you notice that all the forms are almost the same. So if you added up the two equations, if you've got set of both equal to 0, add them up, the beta terms disappear, and you quickly get that n has to equal s plus I. That's the first thing to notice, just by adding the two equations together. Then, otherwise, they're pretty much the same. So plugging that into this, so n's the fixed population, so n's a fixed number. So rearranging that to give the bottom equation, we're getting beta on n beta on n times by s, which I guess we can write down as n minus I minus alpha factorized I is equal to 0. So that's what that second equation becomes. So just factorize the I out and replace the s by n minus I. So that implies that either I is 0, and that means there's no person infected. And if no one's infected, you can plug in here and you quickly get that everyone is susceptible, i.e. that's a situation where there's no disease in the population whatsoever, but it's ripe. But if disease ever entered it at all, there's a chance that people can get infections. Otherwise, this factor here could equal 0, and you can get solutions that way. And so, in this case, let's see. So I is equal to, so let's put dot, dot, dot. So there is another solution there. Just for sake of time, I will just skip it out. So I'll let you worry about it. So there is another solution, and that corresponds to when there's a fixed number of the population that are infected, essentially. And you could just do that by rearranging the equation, making the subject of this one equals 0. So now I know what a critical point is. So if there really was no, if everyone's susceptible and no one's infected, that's critical. So it'd still stay like that. But what happens if we bump it? What happens if someone flies in and gets in with a few infections? What's going to happen? Is it going to fall back to our critical point, or is it stable, or is it unstable? Is it going to move somewhere else instead? And a way to work that out is we need to linearize the system. So the way to linearize the system is just take the different partial derivatives. So just work it. So if we call this, say, f and g, then I want to take the partial derivative of the first one with respect to the various variables, so s and I, and the second one with respect to s and I as well, to form a matrix. Again, linear systems just correspond to matrices. So the partial of this first one with respect to s is equal to, say, minus beta I on n minus alpha, that's the respect to s. Respect to I gives you minus beta s on n. Take the second one, respect to s gives you beta I on n. Respect to I gives you beta s on n minus alpha. Now that's what it is. That's what the linearization is in general. So in particular, at our first critical point, so when everyone's susceptible, s is n, and when no one's infected, this matrix here becomes, so I'll just plug them all in. So getting minus alpha, 0, minus beta, that's a positive, isn't it? So beta minus alpha. So, and again, to work out stability, like everything else, you have to work at the eigenvalues. Now, this is a triangular matrix, and so for triangular matrices, the eigenvalues that really is to work out, they are just the values on the diagonal. So these are my eigenvalues, so minus a and beta minus alpha. So alpha and beta minus alpha. So alpha and beta are both positive numbers for it to make sense. It's a physical situation. So we've got two situations. So this first one here is definitely negative. So we've definitely got one negative eigenvalue. Depending if beta minus alpha is positive or negative, you get two different situations. So let's spell them out. So if beta minus alpha is negative or positive, you get two different situations. If it's equal, it's that really in-between case, you've got no idea. You have to analyze a bit further. So the boundary case is tricky. So we'll just ignore it essentially because it's indeterminate. So if this is negative, that would tell you've got two negative eigenvalues. That tell you no matter which direction you're coming from, it's always going to be shrinking in. And so that would suggest that it's a stable node. If one's positive, one negative, that would suggest it's an unstable. And you've got one in each direction, one positive, one negative. It's called a saddle point. So if you just think through the physical situations before I finish up, B here is how quickly the infection spreads. A here is how quickly people recover. So if beta minus alpha is negative, that would suggest that people will recover quicker than the infection spreads. So in that case, if there's a small amount of infection, then the people will recover quicker than the infection spreads, and so it quickly goes back to no one being affected, and that's why it's stable. That's really the physical interpretation here. On the other hand, if things get infected quicker than people get to recover, it means that as soon as a little bit of infection comes up, it just blows out, and that's why it's unstable. And so what happens, if you do further analysis here, the other critical point, which is the one I didn't work out, when this first one is stable, the other one's unstable, and vice versa. So it's only ever one stable critical point and one's unstable. So if beta minus alpha is positive, it means that if there's a small infection, it quickly disappears from this point and it gets attracted towards the other critical point instead. That's the idea of stability. And so although we have not solved the equation at all, this approach, it does show qualitatively what will happen in different circumstances. And therefore, try and understand the difference, beta minus alpha, is going to be critical to trying to understand this. And therefore, trying to change this value is important. So if you can do vaccination, for instance, so vaccination will change, will reduce beta. So you vaccinate some people in the population, then beta goes down. There's less people that you can actually infect, so to speak. Not that the CIS model isn't really vaccination idea, but that sort of idea. Or if you can stop people moving around, that reduces B and therefore can help stop the infection. That's where these things come from. So I hope that helps you just give you a rough introduction to this sort of stuff. And I like the concrete example, just to give you a sense of where it can be used. And if you do Google for SIR model, so SIR model, it gives you many more variations of this, and you can see there's just the first of many. Before we go, do you have any other questions you guys like to do at this point in time? I'll do the non-homogeneous cases next week, and that'll be on the Wednesday. So I'll do that on the Wednesday, and I'll continue doing these things on the Wednesday wherever I can. So I just got a meeting tomorrow, unfortunately. Okay. So if you've got no more questions, I'll stop the recording and I'll see you next week.